Okay. Oh, I should make sure that it's recording my voice. It is, hooray. Okay. Chem 12. And we want acid base 2. There we go. So we are right now on page 23, 23. All right. So quick review of strong bases. Strong bases are most often what? Tell your partner. You should know this by now. We spent all of 5.1 talking about it. Or sorry, all of Unit 4 talking about it, and we reviewed it just a few days ago. Metal hydroxides. These fit the Arrhenius definition of a base because what do they do? Tell your partner. And remember, it's Arrhenius. So they release OH minus ions in solution. What are some examples of these metal hydroxides? NaOH, LiOH, SrOH, 2. How many strong Bronsted-Lowry bases are there? There are 2. I would like everyone to tell their neighbor what they are. You might need your pink booklet. Anyone need to borrow one? They are O, 2 minus, and NH2 minus. Is good? Okay. Weak bases. Now, we have talked about them very, very briefly before, but we're going to go into more detail here. All weak bases are Bronsted-Lowry bases. Which means that they are what? Something that starts with P and then something that starts with A. Bronsted-Lowry has to do with whether you proton acceptors, yes. So for example, here is ammonia, which is a Bronsted-Lowry base. And what is it doing? It is accepting a hydrogen from the water. So a hydrogen transfers from the water onto the ammonia, and we end up with NH4 plus. Okay, so it accepted a proton. And what were we left with after water gave away a proton? We ended up with OH minus, and this is why ammonia is a base. Okay, because it releases hydroxide upon reacting with water. Now, with weak acids, we could cheat and leave the water out of the equilibrium, right? We could just have it dissociate into H plus and A minus. And that's because weak acids not only fit the Bronsted-Lowry proton donor definition, but they also fit the Arrhenius definition where they simply release H plus ions in water. So that is all our weak acids are proton donors and they release H plus ions. But bases, you cannot do it. If you take a look at NH3, how can you get OH if you just have NH3, if there's no water around? Can you make it happen? No, you can't, right? Like, where's the O coming from? There's no O. And by the way, if you're interested, this question mark exclamation point, punctuation trivia, it is known as an interrobang. Isn't that an awesome name? Anyway, that's an interrobang. It can be also written like this. One of my favorite pieces of punctuation. Okay, I don't know what was wrong with you while I was writing this. NH3 ain't got no oxygen, so it can't very well just release OH. At any rate, all equilibria involving weak bases must involve water or another Bronsted-Lowry acid as a reactant. Okay? Because this is the equilibrium constant for a base, since weak bases form an equilibrium, we can write an equilibrium constant, KEQ. What do you think we would call the KEQ for a base? KB. Can you please write the KB expression for ammonia? Is that what you got? Good. We left out the water? Good. All right. Now, we're going to find some patterns. This is a little mini lesson in organic chemistry. You don't really need to know organic chemistry. But one of the key ideas just in science in general is finding and studying patterns. So let's try a few of these. These are all weak bases. I would like you to look at all of these formulas and names. And then you're going to answer question 1. What do all the names, other than ammonia, have in common? What do a large number of the names have in common? And what do all the formulas have in common? So take a look at those and see if you can see any patterns. You need the, yes. Just give me a little wave when you're finished. Or a peace sign. Or a thumbs up. Okay, what do all the names other than ammonia have in common? They all end in "-ine". It's pronounced "-ine". What do a large number of the names have in common? They end in amine. Amine. What do all the formulas of the weak bases have in common? NH or N. Okay, so we have NH something. I'm going to put NHX, where X can be equal to 0 or 1 or 2. And I'll prove to you that hydrazine is actually, it's just NH2, NH2. So it really is NH2. Okay, so if you have studied any organic chemistry or biochemistry, which some of you might have done in biology, or maybe you did it last year in Chemistry 11. I know I did not get to much with my class in Chemistry 11, but you might recognize a functional group. A functional group is a recognizable collection of atoms in an organic compound. And the reason it's called a functional group is that the particular collection of atoms will give the molecule a particular function. In other words, it behaves in a certain way because of the atoms it's made of. Okay, you don't need to know any of that for Chem 12. Okay, you just need to be like, okay, whatever. But if you go take organic chem, that's what it means. So this particular functional group, where it's NHX, anyone know what it's called? Okay. It's known as an amine. Amine. So we have general categories of amines. We have ammonia, which is just NH3, okay? Then we have NH2, which is attached to something else. Yes? And the something else is often referred to as R, and it just stands for the rest of the carbon chain. At least that's what I make it stand for. I don't know what it really stands for in the world of chemistry. Okay? So it could be anything. It could just be like I could have CH3, NH2. Do you know what I mean? Or I could have CH2, CH3. I could have two carbons attached to it. Or I could have a ring structure attached to it, or any sort of thing attached to it. If I have one carbon chain and two hydrogens, that's called a primary amine. Okay? If I have two carbon chains, or whatever else it happens to be, it could be a ring, and one hydrogen, that's called a secondary amine. And if I have a carbon chain, a carbon chain, a carbon chain, and no hydrogens, that's called a tertiary amine. Do you need to know any of this for grade 12 chemistry? No, you do not. Okay? Totally unnecessary, but might be useful if you're going to be taking biology next year, if you're going to be taking organic chemistry in the future. These are useful concepts: primary, secondary, tertiary. I think I even learned them in Bi 12. Or maybe it was primary, secondary, tertiary structures of proteins. That could be. But anyway, useful in chemistry and biology. These amine functional groups are found in many organic compounds. Now, what does organic mean in the context of chemistry? It means carbon-based, okay, based on the carbon chain. Can you guess from biology a thing that starts with A and then another A that contain amine functional groups? Amino acids, yes. The acid part of the amino acid is a different functional group, and it's one that you've probably already seen. It's a carboxylic acid groups, which gives us carboxylic acids. And those are the ones that end in COOH. So if you have this functional group here, that is the carboxylic acid functional group. All the stuff on this page is not part of the Chemistry 12 curriculum, and it will not be tested. However, will it be useful if you go and take organic chemistry to have seen some of this before? Yes. Pardon me, the entire page. Oh, yeah, the entire page. Okay, this page not tested. This page not tested. Okay? But the reason you need to know it is because sometimes I'm going to throw things at you and I'll call it a weak base, but your brain will think it's an acid because it's got hydrogens on it. Yes? Like NH2. Oh, it's got hydrogens. It must be an acid, except for that it's not. Okay, it's a base, which is why we're going through this whole process here. So when amines react with water, water is the proton donor, and the amine is the proton receiver. And if the amine is the proton receiver, that makes it a what? That makes it a Bronsted-Lowry base. So the amines are Bronsted-Lowry bases. So for all of these, water gives a proton and the amine accepts one. You end up with a plus charge and one extra hydrogen. Hydrogen goes over here. You might say to yourself, where is that hydrogen going to go? If you have no idea, you can just stick it on the end. But chances are you'll actually be given the formula anyway. Okay, but if you need to, you can just stick the hydrogen on the end. When in doubt, stick the hydrogen on the N. Okay, we've got another one here. H plus, H plus. Where do you put the hydrogen ion accepted from the water? On the N. Okay. Try writing the equations for the reaction of the following amines with water. So you give it a try yourself. Okay? Okay, and you can check your answers up there. Okay, so now you know what to do if you see an amine group. Just stick the hydrogen on the end, and your other product is going to be the hydroxide ion. Okay? Oh my goodness, look who's back. It's our little old lady, and she's still weak. Okay, except that it's not a weak acid this time, so we need something a little bit different. She is going to her home base. Ha ha. Home base. Yes? And she still has her bag of rice. Yes? And she picks up her bag of rice and she makes it to home base. And the crows are not eating the rice anymore and saying, caw, caw. What are they crying? They're crying, kebab, kebab, because they found some kebab on the ground. KB. Kebab, kebab. Okay? Pardon me? I know, right? Anyway, it's not really a story that makes a huge amount of sense, but you've got these little pictures. I'm like really quite proud of like the little crows on top of the kebab. Like no, I didn't actually make the images, but like I found some crows that were like PNGs, so they're transparent on the background, and I stuck it in front of the picture of the kebab. Anywho, super fun. Okay, I know I'm a little too obsessed with this story, but I want you to remember that the little old lady makes it to her home base. The crows need to eat the kebab. So if you are working with a base, you must use KB. So many students, when working with a weak base, will try to use KA instead of KB. Oh, it pains me. Every time I see it, I'm like, the question literally says the weak base, blah, and then they give me this whole thing where it's acting as an acid. And I'm like, it says base in the question. Anyway, so make sure, if you don't want me making that horrendous noise ever again, that you read the question. And if it says base, it's going to accept a proton. Yes? And you're going to use KB. Okay. So every time you see a substance, you're going to ask yourself, is it an acid or is it a base? Is it strong or is it weak? And you now know how to recognize all your acids, all your bases, whether they're strong or whether they're weak. And if you can't remember, you can go back and look it up again, okay? So just because a question asks you for H+, do not assume you are working with an acid. You could be working with a base. You'd have to find hydroxide and then convert it to hydrogen. Yes? Or if I ask you for pH, you'll just end up with a high pH because you've got a higher hydroxide concentration. Would you guys like to try this question? Give it a go. Are you running base 2 times? Accepting an H from water, that doesn't what will water act as? Water acts as the, yeah. That's just water. When you do water. Yeah. Uh-huh. Yes, yes, yes. Hi.
How do I go from concentration of hydroxide to
Concentration of hydrogen. Kw equals H plus times OH minus. Do you remember what Kw is?
always working? Or is
10 times 1 times 10 to the negative 14.
and that equals concentration of OH.
OH times concentration of H. Yeah. Yes. Which arrow chart thing? Oh, yeah, absolutely. I can do that. Yeah, let's just do that down in the corner here somewhere. We have hydrogen, concentration of hydrogen, concentration of hydroxide. Thank you for asking. I'll turn the lights down so you can see a little better. How do we go back and forth between hydrogen and hydroxide? Kw is equal to hydrogen times hydroxide. And what does Kw equal? 1 times 10 to the negative 14. How do we get from, oops, I shouldn't have done double-headed arrows there. I should have done one on one side and one on the other. How do I go from hydrogen to pH? pH is equal to negative log of concentration of hydrogen. pOH equals negative log of the concentration of hydroxide. I've not given myself much room there. I'm sorry. And then to go back up, how do we go from pH to H? Yeah, concentration of H is equal to 10 to the negative pH. Concentration of OH is equal to 10 to the negative POH. And how do we go back and forth between pH and POH? pKw is equal to what? pH plus POH, and pKw is equal to 14.00. There we go. Yeah, so basically everything you learned in acid base 1 is fair game. In acid base 2, there will be less of a focus on like solving for the acid, but you know, could do. Okay. Yes. Huh? Oh, but I've got 0.1 here. Right? So I've just multiplied that by that. Yeah? Did you guys get 1.5 times 10 to the negative 9? Yay! I did it right. Woohoo! It's always exciting when I don't make a boo-boo. So how do we feel about that? Fairly straightforward, very much like acid-base part 1, just with that extra step there. Okay, and there is no table of KB values. Okay, so either the question is going to have to give you the KB value, or there's a way that I can show you how to calculate it from a Ka value. Let's see. Do you guys want one more example of the KB, or are we good? We're good? We can move on? All right. The only thing is, like, if you get a formula like this, and you're like, oh my gosh, I don't want to write out that whole thing, you could say, I'm going to say, let B be the formula for morphine. Yep. Okay, so what you would do then is you would say, I'll just give you the first step in this. Okay, you would say, let B represent the formula for morphine, and then you would have B, which is your base, plus H2O goes to BH plus OH minus. Oh, this is a different kind of question. It asks you for the KB. Do you think you could solve for the KB? What is the KB if the 1.50 molar solution has a pH equal to 10.5? Ooh. What do I still need to use? Yeah, it's a weak base, so I'm going to use rice. And I'm also going to use KB. Yes? Okay. Can you figure out that first line of your rice table? In this case, the KB is our unknown. So can my change in concentration, remember the C stands for change in concentration. Can the change in concentration also be an unknown? Can you have two unknowns in one equation and solve the problem? No, you cannot. So if this is unknown, then this one has to be known. Oh. What information do we have that will allow us to find that change? We have the pH, yes? So I think over here, what could we do with our pH? We could take our pH and we could turn it into H plus. Now, is that going to help us with our equation here? Do we have H plus in our equation? In our reaction? No. What do we have in our reaction? We have OH. So we either have to go to hydrogen and then to OH, or the other route to go is from pH to POH, and then to OH minus. Do you guys have a preference? I always find POH is easier. So POH is equal to pKw minus the pH. So that's 14.00 minus 10.5. Is it 10.5 or 10.50? Just 10.5. Okay. That's fine. So we now have 3.5. So the concentration of the OH then, how do we find concentration of OH from POH? 10 to the negative POH, which is equal to 10 to the negative 3.5. So that's going to be 3.16 times 10 to the negative 4 molar. Where does that value go in your rice table? Yeah, it goes, it's the equilibrium concentration of hydroxide. Obviously, it's not the initial concentration because the initial concentration is 0. So we have to fill in our 3.16 times 10 to the minus 4, which means that our change in concentration is how much? Plus 3.16 times 10 to the minus 4 plus 3.16 times 10 to the minus 4, 3.16 times 10 to the minus 4, minus 3.16 times 10 to the minus 4, and we get 0.4968. 0.14968. 9, 7. There we go. I'm going to separate this out a little bit so it looks a little bit clearer what's with what. So our KB then, so we've done our rice table. Now we have KB. Could you solve the rest of it? Do it. Okay. What do you guys think? Have I got the answer right so far?
Yes.
Okay. Now, what do we think about significant figures? Oh. So we have to go back to our original numbers here. We've got a 1.50 and we have a pH of 10.5. How many sig figs in 1.50? 3 sig figs. How many in a pH of 10.5? 1 sig fig. So we need our answer to have 1 sig fig. See how we're reviewing all these concepts, right? Oh. So that's just going to be 7 times 10 to the negative 7, and that is our final answer. Is good? Yeah, we did have to do that second example because it had enough different stuff. Okay. Ooh, do you guys think you could do this one on your own?
Yeah.
Give it a try, okay? This is the third variant where you're finding the initial concentration, okay? You've done this for acids, now you're doing it for a base. Yes. Okay, so we don't make fun one day. It's two base. That means water is not acid. So what are you going to end up with? Okay. So what did water do? Or either way. Or is it an acid? the charge? Plus. That's it. Uh-huh. There you go. Okay. Done. It's so fun. Yes. Sorry about that. Initial prospect. See prospect. Yeah. Thank you. You just dump it all in there. Perfect. Good stuff. Now, do you guys remember the algebra trick to make solving this a little bit easier? Don't just take this up here and multiply it out. You're going to take this one up here, but you're going to bring this one down here, and that makes the solving so much easier. Okay, because you can solve it by putting that up there and multiplying everything out, but watch. If we go like this, we say, oh, CI minus 1.4 times 10 to the minus 4 is equal to, oh my God, I've not given myself enough room, have I? 1.4 times 10 to the minus 4 squared. And now I'm going to drop this 8.40 times 10 to the negative 7 down here. And now I don't have to multiply things out. And I just have to do that and then do an addition and then I'm done. That makes my algebra way easier than just bringing, if I just bring this up here and multiply it out, then there's more algebra steps. Yes? It just makes it a little messier. This just makes it faster. Both will work, but you can save yourself some pain by doing it this way. Plus. Did you guys get 0.2502? Probably need to check some sig figs there though, right? So that's going to round to 0.25. And because it's a concentration, our unit will be molar. Remember, when we refer to the concentration of an acid or the concentration of the base, it is always the initial concentration that we want. Okay, so if I ask you for the concentration of the base, I want the initial concentration. If I ask you for the concentration of an acid, I want the initial concentration. Sometimes they'll be the same, but once we've rounded, but sometimes they won't. And that's it for that. And we are almost out of time, aren't we? What time did we run to today? 1:41? We're almost out of time. So for part A, please try to write the ionization of the base using the actual formula rather than saying let B represent the formula of the base. This will give you a chance to practice putting your hydrogen onto the N. Okay? Now, since these are all fairly much the same, you might just choose to do the first two. Do you know what I mean? Right? You might be like, okay, you're going to be calculating the concentration of hydroxide. the H plus, the POH, and the pH. Part B, you're just going to do 6 and 7 unless you feel like you need more practice, okay? Because they become very, very similar after a while. Part C, do only 10 and 11. Okay? And that's it. Okay, so for homework, it's 1, 2, 6, 7, 10, 11. Okay, page 29. And to be fair, if you really know what you're doing, you could just do 1, 6, and 10. You know what I mean? Because they're just like repeats, but. So if you're really pressed for time tonight, you could do 1, 6, and 10. But if you think it's going to make it stick in your mind better, do the 2.